And we're back. Welcome back. Uh, Today we're joined again by Charlie. I was heard that we weren't giving him Charlie enough airtime in the 341 lecture, so giving Charlie a little more airtime, we might swap over to Jules at some point. Who's chilling, looking out the window, looking at some burbs. Nice. Today. So last time we covered graphs. Love graphs. Graphs are awesome. Today, we're going to talk about disjoint sets. And this is one of my favorite lectures to do because it's brought to you by a good friend, AxeCop. So if you're unfamiliar with AxeCop, AxeCop is a comic that was written by a 5-year-old and drawn by his 29-year-old professional artist brother. Um, and it's amazing. It doesn't make any sense. I mean, it makes a kind of 5-year-old sense, right? So it's just kind of it's every panel is a new weird thing being introduced. Characters come and go, just like just in and out. Some of them stick around, Moon Ninja Warriors and so on and so forth. And it's a brilliant comic because it's insane. It's just weird. Uh, yeah, so one of the themes brought through by the 5-year-old author is friendship and teamwork, which I love. Like, there's no reason this 5-year-old had to make it about friendship. Oh, and also like incredible violence, like large amounts of violence. Um, but about teamwork, about, hey, you seem cool. Do you want to join teams, right? And so the whole idea of there's this prevailing theme of when Axe Cop meets somebody, that person is either a villain or is going to join his team because it's a good guy. It's very binary. It's very, are you a superhero or are you a supervillain? That's it. That's all. Why would you need other characters? And really, why do you need other characters? You don't. You don't. 5-year-olds get it, man. 5-year-olds get it. In fact, when I was doing NLP research and we had a really difficult linguistics problem, we would all one of the professors had a 7-year-old at the time, and we'd always ask the 7-year-old, "What do you think of this?" They'd always be right. Be like, "We're overthinking this so hard." 7-year-old's just like, "Yeah, dummies. Of course it works like this." Anyway, uh, so yeah, the purpose of disjoint sets is to group data that isn't in a set in the sets. So the idea being that so we're talking about sets here, which if you remember way back towards the start of the semester, sets are used to represent membership, right? Sets don't have duplicates, so don't no duplicates here, right? Everything that goes into a set is a unique entity. And so what we're trying to do is we have a bunch of unique entities that are going to start forming teams. And so the whole point of disjoint sets is how do we keep track of um what teams exist, who's on those teams, and how can we allow teams to join forces and do all of this very efficiently. So we're looking for very, very, very high performance here. All right? So, and so the reason they're called disjoint sets is because each unique individual may only be on one team at a time, right? You can't be on bad guys and good guys. You got to be on bad guys or good guys, right? That's the thing. Also with disjoint sets, once you join a team, you can't leave. I don't think. Even though it's not hard to implement, but anyway. Why do we care about disjoint sets? Disjoint sets. I don't know like why I just like slip into. Anyway, why do we care about disjoint sets? Well, Kruskal's minimum spanning tree algorithm is a graph algorithm that comes up with a if given a graph, how do you find a tree that visits all the nodes in the graph? Moreover, how do you find a tree that has visits all of the nodes in the graph and has the lowest weights? Okay, that's a minimum spanning tree. Minimum because lowest weights, spanning because it visits everything, tree because it is a tree here. So if we look here, this node on the little bottom right area, that would be the root of our tree. Or potentially this one over here would be the root of our tree. Actually, there's a bunch of different things that could be the root of the tree. Anyway, for this particular one. It's also used for graph cycle detection, right? So what you do is you start off with all the nodes, and then as you detect cycles, they get put into teams together of nodes that belong to cycles. Huh. Hmm. It's so appropriate. We just talked about graphs and graph cycles. Excellent. All right, time to find Axe Cop and cut off his head. That's what we're gonna do. We're gonna find Axe Cop, cut off his head. I apologize if you find any of this a little particularly violent, but in my defense, a 5-year-old wrote it, so this is evil Sakurang. Um, it's just so good. Anyway, so we have all of these different elements, A, B, C, D, E. They're all independent. And so we have teams S1 through S4, right? S3 has 2 members on its team. Excellent. This find operation is given an item, tell me what set it's in. So I could say find E, and that would return set 2, team 2. Nice. And if I said find D, it would return set 3. Right? Pretty straightforward, hopefully. All right, now it's union. And each of these slides, I have to read through the comic because that's what we do here. That's the rules that I've made up. So Axe Cop saw that the Moon Warriors were very good fighters. I mean, obviously, they're Moon Warriors. We need you to help us fight the Vampire Baby Man Kid. Vampire Man Baby Kid. He turned our family into bats. Like you do. He's too scary for us to fight by ourselves. So Axe Cop and the Moon Warriors join forces. We could be an unstoppable team. To be continued. Ooh. Ooh, joining forces to fight the Vampire Man Baby Kid. Not Vampire Baby Man Kid or Baby Vampire Man Kid. Vampire Man Baby Kid. VMBK, guys. VMBK. Don't forget it. So, what we're doing here, the union is the team merge operation. We had 2 teams here. We had Team Axe Cop. We had Team Moon Warriors. And we said we want to union them together to make another team, another bigger, awesomer team. Now, typically, when we do this, one team absorbs the other team, right? So if I have, in this example, I'm unioning S1 and S2. After I do the union, I can call the result of that union either S1 or S2, but one of the 2 teams gets absorbed by the other team. And let's be real, as cool as the Moon Warriors are, they got some sort of ninja vampire thing going on. As cool as they are, they're not Axe Cop. So Team Moon Warrior joined forces with Team Axe Cop, resulting in Team Axe Cop. This is actually an important insight for later. The Axe Cop part especially. This is so much weirder to do online, this lecture. It's just weirder, especially like a recording. It's strange. All right. Something simple make set. So, just basically every time you add a new element to disjoint sets, so like your insert operation is I want to add this new unique element and give it a team all on its own, right? So if we have the disjoint set data structure and it has a whole bunch of members and teams that those members belong to, if I want to add a whole new member, I just say I'm going to add I'm going to add member Sakurang, and I'm just going to put member Sakurang on team Sakurang, right? So every time you add an element, it's just on a team by itself. So the only way that teams form is individual elements are added and then their teams get union together to make larger teams, awesomer teams. So, as if we haven't discussed this enough, what kind of data stores are we going to use, guys? What kind? We're going to use Tupperware, sandboxes, pelican beaks, very large socks, arrays, ancient chests excavated from dank not tombs, hot pockets, link structures, oversized Pez dispensers, a suspiciously heavy cello case. Chalky milk? I learned that one. I think it was from 341. I learned about chalky milk, which I love that this can make you guys feel old. Has been around since 2012. That is a 9-year-old meme. Yeah, yeah. Just don't tell me what you were doing in 2012, because that will make me feel old. Okay. So you guys are becoming data structure masters. I could just give you the answer. I could just tell you what the best thing is. That's not fun. And also, I don't think it's necessarily the best way of to learn is just have me dump answers on you. Um, so I've described the challenge. We have make set. We have. Oh, also I didn't talk about make set. This is the origin story of Axe Cop, right? He was just at the scene of a fire and he found the perfect fireman axe and he became Axe Cop and he needed a partner. That's it. That's the best origin story. There's no radioactive spiders. There's no, the son of Earth or any of this stuff. Or it's just a dude finds an axe and he goes. That's what you want to see. All right. So, the instructions here are difficult because you can't work together with the people around you because we're not in a room together. But what we can do is you can type your typies into the text chat and start thinking about how do we implement this. I'm actually gonna let you guys run with it for a few minutes to figure this out because I don't want to just it's complicated enough. And so when you come up with answers in the chat and when you're thinking about your answers, think about efficiency as well, right? Um, this is trivially easy to implement in linear time. It's like you can implement it. It's just will take linear time to work. Um, so yeah, think about what we've done this semester, and I'll give you a clue. Don't go too far down the hash table route. Feels like a hash table thing. Feels like I get that. It's not. It's not a hash table thing. All right. So this is the tryouts. Uh, yeah. Anyway, I'm gonna pause. Oh. Okay. So we've had some ideas. Let's talk about it. So what if we use an array? So here we have 13 items. We're gonna say that each item, its ID has a unique ID, which will be its slot in the array, right? So everything has a unique ID. Its ID is 0 through 13. Cool. Then what's actually stored in the array is the team that each element is on. Okay. So what we do then is we could say, well then, so how does find work? Well, remember, find is given the ID of an element, go to its spot in the array and look and see, or no, sorry, given the element, tell me what team it's on. So for here, it would be go to that spot in the array and look at what you find there. How fast is that? Looking into an array? This is just constant time, right? We just go wham right there. We don't have to scan anything else. If I ask you what team 5 is on, you'll go F. You don't have to look at anything else in the entire array. You can just look at index 5. Boom, it's F. All right. What about what if I told you to union sets or teams E and Q? How would you go about that for this one? Well, uh, we have to find all the members of E and Q. How do we do that efficiently? Well, we have to scan the whole array. We have to scan the whole array. Right? To find every member of E, we have to scan all the way from 0 to 13 and find all the members of E. And so what we would do in this case is we'd say, all right, if we're going to union E and Q, we're going to call the resulting set Q or E. It doesn't really matter for this particular case. So what we'll do is if we're going to call the resulting set Q, then we'll go look at every instance of E and change it to Q. Aha. However, that's linear time. That is not the answer. We can do better. We can do better. Also, make set is just add another element to the end, which is fine. And you'll be like, well, but that's, what if you have to double the size of the array and blah, 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 blah. We'll actually talk about why that's still constant time later. What? Chill out. So how does it work? First of all, Axcop was asked by a reader, what's your favorite food? Axcop eats only cake, and it's a birthday cake with a candle of Axcop on it because that is his favorite food. I mean, and that's all he eats. That's all he eats is a birthday cake every day with a little statue of him on top. Like, that's so good. That's the correct answer. I thought you could have a better answer, but you can't. All right, find. It's an array lookup. Big deal. Union. We have to search the whole array. Not our favorite thing. And then make set is constant. We just write a new element to the end of the array. All right, what about a link structure? So this one's a little bit trickier. The biggest thing to note here, I'm going to actually take away the slide, and we're going to go back to Charlie. Is Jules in his bed? Oh, he is. We might switch to Jules momentarily. The biggest thing to remember about this method is that every team is named after one of its members. Every team is named after one of its members. So, if Jules and Charlie and I are on a team together, we're on Team Jules, or Team Charlie, or Team Ben. The team has to be named after one of us. All right, that's the big takeaway here. All right. So before you start trying to understand what's going on with the slide, remember one of the members of a team is also the name of the team. Got that? Got it? Got it? It's very confusing to people if you don't take that into account. All right. So, in this case, it's the same idea. Every element's ID is its array index, right? So we have 14 elements here from 0 to with IDs from 0 to 13. Cool. If I'm on the team named after me, I have -1 stored in my array index. Okay? So what team is 6 on? 6 is on team 6. 4 is on team 4. 1 is on team 1. Nice. So, and that also kind of makes them the root of this linked structure. Okay? Now, sets become regular trees. And really remember back to regular trees. Regular trees are just, they're not binary trees. They're trees where each node can have any number of children. Each node can have any number of children. The weird thing about these trees is that when we represent trees typically, we represent if we're going to get rid of child pointers or parent pointers, we usually will say parent pointers are optional. Here, it's only parent pointers. You're only pointing your parent. And so you can reconstruct the tree by scanning this array and putting together all the parent pointers to actually see this, right? So what we're seeing here is that 4 is the root. Actually, can I get my laser pointer thing? That's right, it's L. 4 is the root, but we only know that because, well, we know everybody's a root because all of the roots, we know their roots because they're -1, but we only know that 2 is its child because when we look at 2, it says 4 is my parent. So what's being stored in these array slots are parent pointers. Effectively, they are effectively parent pointers. Now, we simplified it because instead of actually like having them be pointers, they just hold the index of their parent, right? Because everybody's ID is their array slot. So 2 is saying 4 is my parent. And so we hop over to 4 and we see, you're the root here. And therefore, if I ask 2, what team are you on? 2 will say, oh, I'm on team 4. Because it'll say, I'm on team 4. Or rather, it will say, I'm on whatever team 4 is on. And then we ask team 4, or we ask 4, what team are you on? 4 looks and says, oh, I'm -1. I'm on team 4. Therefore, we can find out that 2 is on team 4. Some of you are like, oh, this sounds recursive because I just make a recursive call to what team is my thing on, and that would be correct. For 7 says I'm on whatever team 8 is on. 8 says I'm on whatever team 9 is on. And 9 says, oh, I'm on team 9. Therefore, 8 is on team 9. And 7 is also on team 9, right? So these are all parent pointers. So this is a linked structure. It's stored in an array, but it's still a linked structure because those indices are technically memory locations. So it's a little simplified because we're using array indices, but not that much. So how fast does this work? All right, let's think about the operations. Find. How fast is find? Well, what's our worst case? Our worst case is everybody's on the same team, right? And our worst case is that everybody's on the same team and I am at the very bottom of the tree. And so the worst case here would be, for instance, if 13 had -1, 12 had 13, 11 had 12, right? And so if I'm over here at 0, I would say, 0, what team are you on? And 0 would say, well, I'm on team whatever team 1's on. Team 1, what team are you on? I'm on team whatever team 2's on. 2, what team are you on? I'm on whatever team 3's on. And so on and so on and so on. And so you have to hop through the whole thing. So worst case, it's linear. How often are we going to have that worst case? As of yet, we haven't thought about that, but it is the worst case, so we'll say n for now. All right? Later, we might try to prove that we can get that the worst case is infrequent or actually not even that bad. But for now, we'll say linear. Oh, they just all pop up. Well, okay, so then union. If I say union team 4 and team 9, I just go to team 4. I just go to 4 or 9. So if I say union, if I want to make 4 the new leader, I go to 9 and I set its -1 to be 4, which effectively adds a parent pointer running from 9 to 4, making 4 the new root. Or I could go the opposite way. It doesn't really matter for this at this point. If I say, oh, okay, I want to make 9 the new root, I'll switch 4's entry from -1 to be 9, and then boop, I'll have a bigger team. Nice. Make set is still just easy as well. Okay, so we have an array-based method and a tree-based method, a linked structure-based method. So we're going to talk about those in a second and try to get some optimizations because I told you linear was like the easy. We don't stop at easy. We don't. We don't. All right. Would you rather? Oh, a would you rather's about to hatch. All utensils are sticky versus all videos have audio that is 3 seconds out of sync. That's the would you rather. Fun story, the first time I did this would you rather, one student blurted out, I would rather just leave than have to answer this one, which made me feel good. It made me feel good that this was a good would you rather. Anyway, I'm going to pause. Ah! And we're back. I bet that was a lovely conversation. I hope I hope some of you tried to get out of the audio thing. That always happens. Someone's like, well, if I'd rig up 3 videos and I mute 2 of them and then I'm sure you all tried that. No. All right, let's try to make it stronger. But first, let's talk a little more Axe Cop because why not? So Axe Cop doesn't just have a patrol car. Come on, come on. Axe Cop has a Tyrannosaurus Rex that he rides. With Gatling guns for arms. Axe Cop couldn't settle for those little arms. So he has Gatling guns that he controls with his little arms. If you try to ride him and you're not Axe Cop, he has spikes that will stab you if you're bad. I think Wexter is the name of the T-Rex. Why is this what I can remember? I don't understand. You ask me when the project's due, I'll be like, on a Tuesday? But if you ask me, what's the Tyrannosaurus Rex and Axe Cop's name? Yeah, Wexter, for sure. I think it's Wexter. I don't think it's Baxter. It's something really awesome. And their worst enemy is a lamp that comes alive early in the morning. Uh, which, again, it's just gold. Anyway, we like the linked method because it has a fast union. And we like the array method because it has a fast find. So let's suppose we go with the linked method. How can we speed up the find method, right? So we have this linked method right here, right? And find is getting us down. So how can we improve the performance of find without hurting the performance of union? And this is a fun puzzle. So I'm going to give you guys another break to think about it. Ah! Okay, we're back from pause time. So earlier, when we were talking about doing a union, I said, look, if I'm unioning 4 and 9, I go to them and I say, well, let's make 9 the new team leader, the new team mascot or whatever. And I said it doesn't matter at this point or something like that. Let's think about it. Does it matter? Does it matter who the new team leader is? Well, let's look at this case, right? If I have, can I draw on here? That would be amazing. Of course I can't. Why would I be able to draw on here? Oh man. Oh, we're gonna draw on here. I'm gonna make it happen. All right, we're back. Now we're on Jules' cam. This is like up close and personal with Jules. It's his disembodied head. It's like ask Jules question. Ask the disembodied head of Jules any of your questions, and he'll help you sort them out. Because that's what Jules is here to do. He's here to be a disembodied head of cat wisdom. It doesn't matter how much I pull the camera back. He's still just a disembodied head of cat wisdom. Yes, hello, sir. There he is, coming into focus. All right, so we figured it out. We drew on the powers of MS Paint. So the question is, I'm gonna draw an arrow, right? Do I draw the arrow in this direction or do I draw the arrow in this direction? So what do I get with the different situations? Can I make the weight of these lines like not awful? Excellent. So if I make 4 the root, I get 4. This is going to be great. I get 4 and then I'll have 2 underneath it, and then I'll have 9 underneath it, and then 8, and then 7. By the way, I'm left-handed, writing with a right hand mouse with my right hand, so give me some props for that. Okay, so what is the height of... So our worst case is going to be the height of this tree, right? So our worst case is going to be 7. 7 has to make 1 hop, 2 hop, 3 hops. This is a 3-hop tree. What if I make 9 the new root? Well, then I have 9 up here, and then I have 4, and then I have 8, and then I have 7. Nice. So, how many hops? What's our worst case again? It's our buddy 7. Whoops, 7. And how many hops does it have to make? 1 hop and 2 hops. Huh. Okay. So, who should I pick then? Based on what criteria? Well, what I should do is I should pick the new team leader to be the leader who has the est tree, the biggest tree. But on what grounds? Size or height? Size or height? Size or height? Chat? There's no chat, but I'm giving you guys time. Chat? Size or height? Size or height? If any of you answered, it doesn't matter. Both work. Well, I scared Jules. I scared Jules. But applause to you. It doesn't matter. You can pick size or height. Jules, honey, I'm sorry. Oh, I've offended your cat sensibilities. Oh, no. All right, let's flip back to Charlie. All right. All right, we're back. I got a more dramatic shot of Charlie, just so you know. There he is. All right. So, we can union by rank. This is called union by rank. And we can rank the two teams that are being merged either by size or height. It turns out it doesn't matter. So, remember how we marked leaders of a team with -1? Well, that's fine, but we can be smarter about this and just make it any negative number. If you have a negative number stored in your array slot, you're the leader of a team. But now, rather than have it uh, be the result of the rather than have it just be -1, we're gonna have it be the -1 times the size of the team. So here, if we have 9, 9 is going to have a -5 because there's 5 items in that tree. Team 4 is going to have a -2 in it because there's 2 items in that tree. Excellent. When we merge, the bigger set consumes the smaller set, meaning I take the smaller set's negative number and I turn it into the name of the larger set, making that a parent pointer. The size of the new root becomes the sum of the sizes of the two merged trees times -1. So we're trying, the whole goal is we're trying to keep the path to the root short. So what does the union of 4 and 9 look like? All right, we're going to do this with the greatest of speed. Okay, we're over here. All right, so what does this look like? Well, what happens here is we compare... Oh, I didn't bring the... that's fine. We compare this, which is a size of 2, and this, which is and it'll have -2 in its slot. This is a size of 5. Look how big that 5 is, but it's a -5. And so we look at these and we say, which one's larger? But actually, when we're coding this, we say which one's smaller, because they're negative numbers. And we say, okay, team 9 is the larger team. So what I'll do is I'll change this from a -2 to a 9, thereby creating this new pointer. Ooh, nice. All right. We can also do height. So instead of storing the size, we'll store the height of the tree. When at that point, the shorter tree gets merged into the taller. So how do we change the height here? So again, grab this, go to our friend paint. Ta-da! Oh, this is just beautiful. All right. So we have here, this is a, whoops, 4 is a height of 2. So 4 is a height of 2. 9 is a height of 3. When I merge this into the others, right, I have these two values. So I merge 4 is the smaller one, so I'm gonna merge it. Let's use blue. I'm getting fancy now. So I'm gonna do that. What's the height of the tree? Does it change? No. And we overwrite this with a big old 9. This height actually stays the same. So what does it take for the tree to gain height? What has to happen? In what case, when would the height of the tree ever change? I guess I'll pause. Pause. All right, we're back. Yeah, the height of the tree only changes if they're both the same height. The height of the tree only changes if they're both the same height. Okay. Okay. All right. And so here we go. Oh, I had an animation for this. Okay. Now, let's look at our performance then. So why does this improve the performance of find? So we're going to select all. Can I just select all? And, oh, thank you, MS Paint. All right. It does just what you need and nothing more. Which, that's a thing. All right, so now we have this lovely diagram again. So what was our worst case for find? Remember, we're trying to improve find's performance. I could get out my writing tablet, but I'm kind of having fun drawing like a 5-year-old. Actually, I had much tidier handwriting when I was younger. So how do we want to maximize the performance of find? So it's currently big O of n. And why is it big O of n? Well, because we would have this kind of situation where dot 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 up until this. And so we would have an n height tree. This is so hard. This takes all of my concentration. I cannot talk while I write. So I have an n height tree, right? I can't get my tablet to work with this machine, and I've given up trying. So we're gonna do it live. All right. So we have an n height tree. When we do union by rank, how tall can our trees get? Well, this is a fun question to answer. So let's talk about the worst case scenario. So the worst case scenario is I'm repeatedly merging trees of the same size. The worst case scenario is I'm repeatedly merging two teams that have the same height. And that I'm just doing that over and over again. I'm never ever merging trees of different heights because that doesn't actually add height to them. So I want to ask myself the question, what does it look like when I only ever merge trees of the same height? All right, cool. Well, let's draw that out. So, all right. So, what is it? Let's start at our kind of baseline here where we have two trees of the same height, 1. What happens when I merge them? I get this. Okay. Well, then how do I get two trees of the height 1? Well, I have to I have to repeat that process twice. Right? So I have 2 nodes. And then what I'm going to do is I'm going to do a merge, but because they're the same height, it doesn't matter which way I draw it. So I get this. And if we want to draw that out a little bit more sensibly, we get this up here, which looks more like a standard tree. Okay. So now this is a height 2 tree, which means if I have to merge this with a height 2 tree, I have to find another height 2 tree. And the only way the tallest we can get a height 2 tree with the smallest amount of items is with 4 items, right? And so if I merge this, I get a height 3 tree. And then what I would need to get a height 4 tree is two trees that look like this. So I had to have two trees of size 1 to get a height 1 tree. I had to have two trees of height 2 to wait, yes, height 2 to get a height 3 tree, and so on and so forth. Which means every time I gain one height, I have to have twice as many elements in the tree. Which means every time I increase my height by 1, I'm multiplying the size of the smallest possible tree that could be that height by 2. What is this starting to feel like? If I have a tree of size n, how tall is the tree gonna be? Or if I have a tree with n members in it, what is the largest possible height for that tree? The lowest possible height for the tree is 1. The lowest possible is I do this thing and then I always merge ones into it, right? I always merge one. So I have one, I merge one thing into it. My smallest possible height for any n is 1 because I just keep merging in things like this. Individual values, right? Our worst case is when we merge teams of the same height. So, and then it starts to look like a flower, like this. So this is the goal, by the way. This is our goal state right here. We want flower-shaped trees. This is the sadness, is when they're tall. The thing is, it's log, right? If the height of if I have to double the size of the tree in order to get one more height, that means that the size of the tree is growing exponentially with the height, or to turn it back around, the height of the tree is growing logarithmically with the size of the tree. So if we've made an optimization to union, we've changed the behavior of union to increase the performance of find. So our find still works the same way. You start at one node and you follow parent pointers until you find the root. Now now it's going to do the same thing, but because union wasn't just saying, I don't care which one merges into the other, it merges the smaller one into the larger one, we actually get logarithmic performance for find. And this is huge, right? So if I have a tree of 1,000,000 items in it, my worst case used to be 1,000,000 operations, and now it's like 15 or something. 10, 15, something like that, right? Log base 2 of 1,000,000. Log base 2 of, oh, come on, 19. So we go from 1,000,000 to 19. This is a massive performance increase. Like, it's huge. Just by doing this one little thing of comparing the heights of the two things that we're going to merge. That's awesome. It's like such an easy optimization. The hardest part of that was convincing ourselves that it was logarithmic performance afterwards. All right, what else can we do? I'll give you a hint. I've flashed the slide a few times. So we improved union to make find faster. How can we improve find to make find faster? I'll pause it. Okay, I'm back. So we're going to cache results. What we're going to do is when I'm doing this find, if I say find 7, 7 will look at 8, 8 will look at 9. What I do then is I go back when I'm recursively unwinding, basically. I go back and I say everyone that I looked at along the way, I want each of you to know that you're on 9, which will cause 7 to then be directly connected to 9. So what this does, if we look at our beautiful MS Paints, we will see that if I have a path like this, and this one's the root, right? If that one's the root, then what I'm gonna do is I'm gonna go through this path, but on my way back, I'm going to tell this one, hey, this is your parent. It's like, yeah, I know, I already have a parent pointer. But then I'll go to this one, I'll say, hey, your parent's up here. And it'll go, oh, okay. And then, hey, this one's your parent up here. And so what we're doing is we're taking a structure that looks like a linked list and we're turning it back into this flower shaped data structure. So we've caused our linked lists to bloom into beautiful flowers of disjoint sets. I mean, that's just factual material happening. Um, so yeah, we just tidy up as we go. So here we go. Here's another example of it, where if we do a find for 13 and 6, 12 and 13 and 12 will get their pointers updated to 9, and 6 will get its pointer updated till 9, and we look more like a flower. This one's got a little stem. Oh, oh. So we're making finds. Uh, we're making each find make subsequent finds faster. Okay. Uh, so our union operation was constant time. Was constant, still is constant, because all we're doing is we're adding an if statement to it, not a loop when we do this union by rank. So when we union by size or height, we get trees. We get logarithmically tall trees. So we have big O of log n for those items. However, if we look at average running time, we find that if we do F finds and W unions, meaning I do that many, F many finds and U many unions, it takes big theta of U plus F times alpha of F plus U and U. What is alpha? What is alpha? By the way, doing this average running time, you might be like, wait, do we have to know how to do that? That'll be the last lecture. We'll be talking about that. It's called amortized analysis, but we're not talking about it yet. So suppose we go do a big heavy math lifting and we come up with this answer. What is this? This is the inverse Ackermann function, which is an extremely slow growing function. This function never computes to 4 for any value you would ever reasonably use, right? I mean, let's see. Can I inverse Ackermann? Inverse Ackermann calculator. Do we have it? I don't want. All right, we're not going to demonstrate it. But basically, for any values of f and u that you can come up with, the inverse Ackermann will be very low. It will basically always be 4. If you want like a billion and a billion, it's probably not even 4. It's less than that, right? So we think of if we do path compression and union by rank, we actually get find performance that is so fast it resembles constant time performance. So I love disjoint sets. I love this lecture for 2 reasons. We got AxCop. We got it's a fun little niche problem that we end up being able to do some fairly intuitive optimizations for to get linear time all the way down to very nearly constant time, and for all intents and purposes essentially constant time. So I'll round out this lecture. So Hosta Mia, Lobsterman, Fishy Fish, and all the zombies became Axe Cop's zombie minions. Everybody ended up joining Team Axe Cop. Intrepid. The superheroes left to fight crime. The Moon Warriors have new costumes. They look great. They look great. Presti was back with his family. That's always exciting. And everyone was happy. The end. That ended the Moon Warrior saga, which is very exciting. So I hope you guys enjoyed this lecture as much as I enjoy giving this lecture, even stuck at home with my adorable animals. It's still pretty fun to do, and I'll see you next time.